In this video, we're going to continue talking about linearly independent vectors, but instead of focusing on the definition, we're going to introduce some theory. Now, this was an example that we went through in the previous video, and I just want to point something out about the setup. So we wanted to know if these vectors were linearly independent. So we took a linear combination of these vectors and we set it equal to the zero vector. And we wanted to know if this had only the trivial solution or if it had a non-trivial solution. And to answer this, we solved this system of linear equations. And to solve this system, we formed this augmented matrix. And what I want to point out is that the columns of the coefficient part of this matrix are exactly the vectors that we're interested in. So again, this matrix is formed by taking each of these vectors and writing it as a column. So this is the setup that I want us to keep in mind when we're looking at this theorem. Okay. So let U1 up to UK be column vectors in Rn, and let A be the n by k matrix with these vectors as its columns. So we're going to take each of these vectors and write them as the columns of a matrix. There are k vectors, so this is why A has k columns. And each of these vectors is a vector in Rn, which means they have n entries. So this means here that we're going to have n rows. So A is an n by k matrix. And we're going to let B be any row echelon form of A. And the key here is that it's any row echelon form. It does not have to be the reduced row echelon form. Any row echelon form will work here. Okay, so then U1 up to UK are linearly independent if and only if the homogeneous linear system with augmented matrix A0 has only the trivial solution. So here we have only the trivial solution, and the trivial solution is the zero vector. So this is what we were checking before. And so what's new is that now we're going to check that there is a leading entry or a pivot in every column of B. So here we can just simply count leading entries and see if there's one in every single column of B. And if this happens, then these vectors are linearly independent. Now we can also express this in terms of rank. We can talk about the rank of A. So recall that the rank of a matrix A is the number of leading entries in a row echelon form of A. So the rank of A in this case is going to be the number of leading entries in this matrix B. And what we know is that this matrix has a leading entry in every single column. Well, both A and B have k columns. There's a leading entry in every single column, which means the rank of A will equal k. Now, the rank of a matrix has to always be smaller than the minimum of the two of n and k. So it can't be bigger than k. And so if there's a leading entry in every column, it means it would have to be exactly equal to k. And so again, A has k columns, so this is equal to the number of columns of A. So we can either check to see if there's a leading entry in every column of B, and this is the same thing as checking to see if the rank of A is equal to the number of columns of A. So if this happens, then the columns of A, which are these vectors, are linearly independent. And now, in terms of linearly dependent vectors, U1 up to UK are linearly dependent if and only if the homogeneous linear system with augmented matrix A0 has a non-trivial solution. So this is what we were checking before to see if this has a non-trivial solution. And when we're dealing with homogeneous systems, we know that if it has a non-trivial solution, then in fact it has to have infinitely many solutions. So if a homogeneous system has a unique solution, it means that that would be the zero vector, that it's the trivial solution. So if the solution is unique, it would have to be the trivial solution, 0. So if it has a non-trivial solution, we know that a system of equations cannot have just two solutions, so there would have to be infinitely many. So checking if there's a non-trivial solution is in fact, in this case, the same of checking that if there's infinitely many. So in this case, having a non-trivial solution means infinitely many. So infinitely many solutions. So they're dependent if and only if this has a non-trivial solution, which is the same thing as having, for this homogeneous system, having infinitely many solutions. So that is, and this is what's new for us here, at least one column of B does not contain a leading entry, also called a pivot. So again, the key here is at least one column does not contain a leading entry. And again, we can express this in terms of rank. So in this situation, this would be saying that the rank of A would have to be strictly less than K, which is equal to the number of columns of A. So number of columns of A. So if at least one column of B does not contain a leading entry, then it means that the rank has to be strictly less than K, because that's also the number of columns of B. So the rank of A would be strictly less than the number of columns of A itself. And so we can use these two conditions to check to see if the columns of A are either dependent or linearly independent. So if there is a leading entry in every column of B, which is the same thing as the rank of A is equal to the number of columns of A, then these vectors, the columns of A, these vectors are linearly independent. And if there's at least one column of B that does not contain a leading entry, so the rank of A is going to be strictly less than the number of columns of A, then the columns of A, which are these vectors, are linearly dependent. And so this is the test that we can use. We just have to look and see whether or not every column of an REF of A has a leading entry. Okay, so let's revisit the same example. So we're going to do the same thing again. So we want to know, now here I've actually just relabeled these vectors. They were called V before, now they're called U, and that's just to match the notation here of this theorem. So we want to know if these vectors are linearly independent. So again, the setup is we're going to take these vectors and write them as the columns of a matrix. And we do form a homogeneous system. So here we're going to take these vectors and write them as the columns of some matrix that we're going to call A. All right, so then this becomes our matrix here. This is A. And here I'll form the homogeneous system. But strictly speaking, we don't actually need the system. If we're just checking the row echelon form, we don't actually need the homogeneous system. But nonetheless, I put it here just to remind us that there is a system, an underlying system here. And so again, this notation says that these two matrices are row equivalent. So this is a row echelon form of this matrix here. I just haven't shown the row operations. But again, to be clear, on your homework and also on exams, do make sure you show all of your row operations. Okay, so this is a row echelon form of A, and this is what we will call the coefficient part here, we will call B. And so now what we want to do is just check whether or not there's a leading entry in every column of B. So let's identify the leading entry. So there's one here, here, and here. So what's our conclusion? So we are going to conclude here, and here I'll just use the terminology pivot just because it's mostly just because it's less writing. So there is a pivot in every column of B. And if we want to talk about this in terms of rank, if we want to use that rank condition, then we can check this. We can check in this case, what is the rank of A? So again, how many leading entries? 1, 2, 3 leading entries. So the rank of A is equal to 3. And how many columns does A have? A also has 3 columns. So the rank of A is equal to 3, which is equal to the number of columns of A. And so now, by checking either of these two things, we can conclude using this theorem that these vectors are indeed linearly independent. Now, just for the sake of completion, we can check this condition here again. Does this have only the trivial solution? And the fact that there is a leading entry in every column of B, this is exactly what's actually telling us that there is only the trivial solution. To have infinitely many solutions, you have to have a free variable. Homogeneous systems are always consistent, so we don't need to worry about consistency here. These systems are always, the homogeneous ones are always consistent. And so it's enough for us just to check leading entries. And because there's a leading entry here in every column of B, this tells us there are no free variables. This system has a unique solution, which is only the trivial solution, 0. So again, just to be thorough here, we can also see that this system, again, because there's a leading entry in every column of B, this system has only the trivial solution. So these are the things that we can look at. All right, so what is our conclusion here? The conclusion is yes. These vectors u1, u2, and u3 are indeed linearly independent. So again, just to emphasize here, B is a row echelon form of A. It is not the reduced row echelon form. We don't need to go all the way to the reduced row echelon form. As soon as we have a row echelon form of a matrix, we can tell how many solutions that this system is going to have. If we wanted to actually find those solutions or find the solution, then we could row reduce all the way to the reduced row echelon form. But as soon as we have a row echelon form, we can tell how many solutions a system of equations is going to have. And in this case, we just want to know about numbers. We want to know if it's going to be unique or if there's going to be a non-trivial one, which would mean there was infinitely many. So that's why we can save ourselves a little bit of work, take a shortcut, and just analyze this simply by looking at this coefficient matrix. We just need a row echelon form. We don't need the reduced row echelon form. Okay, one more example. So again, we're going to look at the same example that we did before. And we're going to do the same setup again. So we're just going to directly take these vectors and write them as the columns of a matrix. So here I'm going to get 1, 2, -1, 3, -3, 4. And again, I'll form the homogeneous system. And so when I do row reduce, I will obtain a row echelon form here. In fact, this is almost silly because this was just one row operation. So I could even indicate what that row operation was. So this would be row 2 minus 2 row 1. That's would do the job. This minus 2 of these, this minus 2 of these, and this minus 2 of these. So really, this one was just one row operation. And again, I'm going to, so this is to be clear, this is what we're calling A. And here, this is our row echelon form. So this is not the reduced row echelon form of A. It's just a row echelon form. and I gather up my leading entries. And in this case, so again, to be clear, this thing is in REF. That's enough. We don't need to go to the reduced row echelon form. And what we're going to notice again here, we're going to pay attention to the columns of B, not the rows, the columns. And what we find is that this column does not contain a leading entry, or it does not contain a pivot. So what we're going to notice here is that there's no pivot in column 3 of B. And if we want to think about this in terms of rank, the rank of A in this case, what is the rank of A? Well, there's 2 leading entries, so the rank of A is equal to 2. And this is strictly less, it's not equal to, it's strictly less than 3, which is equal to the number of columns of A. So the rank is strictly less than the number of columns of A. And so with this information, this is enough for us to conclude that these vectors are linearly dependent. Now again, just for the sake of completion, I'm going to talk about the numbers of solutions here. And so we do have a free variable. It's a consistent system with a free variable. That means that we have infinitely many solutions. So if you want to talk about the number of solutions, we can do that. So this has infinitely many solutions. We do have a free variable. So there are infinitely many solutions. So in particular, this means that there is a non-trivial solution. So a non-trivial solution. All right. And so we have concluded that indeed these vectors are linearly dependent. And so the conclusion is, the answer was, are they linearly independent? And the answer is no. 1, 2, -3, -1, 3, and -3, 4. These vectors are not linearly independent. They are linearly dependent. And again, what we were checking for is we were seeing whether or not there was a leading entry in every column of B. Since there was not, column 3 does not have a leading entry, we know that these vectors are linearly dependent, right? This system has a non-trivial solution. It's got a free variable. There are infinitely many solutions. Okay, so I will stop this video here. There will be one more video in which we take a look at some of the theory involving linearly independent vectors.